welcome. Thank you for taking out the time to be here.
Thank you. Thank you for being here. And good afternoon, folks.
Awesome. So let's get started. Groq does something that is different from what Nvidia does. You don't make GPUs. You make this thing called an LPU. Could you tell us a bit about an LPU?
LPU stands for Logic Processing Unit. That is, think of it as a product branding that we have done based on our unique architecture. It's a new paradigm, a tensor streaming processor. It's a general purpose linear algebra accelerator that's Turing complete, that applies to all HPC. Deep learning, machine learning happens to be a linear algebra acceleration problem, and we do obviously exceptionally well at that.
So I believe you have some benchmarks that we can show.
A look at the graph on the right-hand side. The x-axis is tokens per second. So let me set the stage for generative AI. What matters is how one interacts with the AI, with machine learning. What we do is we make machine learning human and making it interact with human beings at human latencies. For doing that, what matters is the time to first word, whether it's spoken or text, and the time to last word. And human beings, the cognitive function of the human beings actually varies quite a bit, whether the response comes in 200 milliseconds or a second or 10 seconds or beyond. So it's Google, for example, shows the first word in 200 milliseconds, or when you do a search. They finish the whole page in 400 milliseconds. It is what keeps human beings engaged. You can imagine if you're talking to someone, if it's voice, and the other person takes 10 seconds to respond, you'll be wondering if the other person actually heard you or not. Interacting with computers, with quote-unquote artificial intelligence, if you want to have a semblance of human interaction, you need low latency. The metrics for that, the ideal ones at the application is time to first word, time to last token. So the x-axis here reflects time to last token. The y-axis reflects the inverse of time to first token. This is a third-party benchmark, so we didn't get to tell them exactly how to plot this. Irrespective, the quadrant at the bottom here, the extreme bottom right, which is green, being in that quadrant, in the right bottom quadrant, is the holy grail. And Groq is the only one in that quadrant. That is what makes machine learning real. That is from 3 months ago. And the way just we work is we won't tell you where we are going, but we just got started. So you can expect better and better things.
So that's very interesting. So just to recap, on the left side, time to first chunk, and on the x-axis we have tokens per second.
Yes, and that reflects time to last chunk.
So that means as soon as I start a query, the first chunk, that's on the.
That's right.
Exactly.
And the bottom one is the rate at which the chunks come, and the higher it is, the better. Again, we didn't choose those axes, so the best way to look at it is the farther you're on the bottom right, the better.
That's perfect. So clearly Groq's killing it, but what's the secret sauce? What's making this?
So it's a new compute paradigm. So I'm sure most of you have heard of von Neumann architectures. That's how computation essentially started. And most of the computation today, general purpose compute, follows von Neumann architecture. I'm putting Harvard and Princeton for the geeks, Harvard and Princeton architecture in the same category. It essentially has a single, what we have, let me frame it the other way. We have a programming assembly line architecture, whereas the existing architectures are more like a hub and spoke architecture, very similar to how cars were being manufactured and the buggies were being manufactured before Ford introduced the assembly line. And the way they were being manufactured, you would have a manager. In the case of the computation, you have a centralized instruction queue and a centralized register that would instruct the various experts, functional units in compute. And you have a central repository where you have to go back and forth to, therefore, hub and spoke. And that creates a bottleneck to begin with. That works great if you have to do highly branched computation, if then else kind of a compute. Very similar to what the prefrontal cortex does in human beings. We are thinking logically step by step. We're looking at what we need to do and what conditions we need to do something else. But your eyes and ears, when they're processing it, most of it is large data being processed in parallel. And by the way, quite a bit of that happens in your visual cortex. Now, going back to the assembly line and the hub and spoke, the hub and spoke limits, because there's a bottleneck, it limits how the data gets processed. It becomes worse. Imagine now you have to go to the warehouse to get the part every time, right? And in the case of the GPUs and CPUs, it's your DRAM. That makes it even worse. What we have as an assembly line architecture, we have a sequence of functional units that are arranged such that they compute as the data. Let me rephrase it the other way around. The data, the instructions come over conveyor belts. The compute station doesn't know where it came from, doesn't know where it's going. It just knows at what time it needs to pick up the data and what instruction it needs to perform. And that way, the data, the instruction, the computation just goes on seamlessly without any bottlenecks. The memory for it, which is the warehouse, think of it as a warehouse, is on the chip, and it is the fastest memory that is 2 orders of magnitude faster than what the DRAM can provide. This arrangement is what gives better latency. It so happens it also gives better throughput per dollar and per watt. Very similar to how, again, assembly line transformed not just car manufacturing, it actually transformed industrialization after that. And that is what we expect our architecture to do on the compute side. My vision for that, for compute, is make compute as cheap as water, because it is going to be as essential as water. To be able to process the mountains of data that we have for the past few centuries, from which we can gather more insight, and to be able to enable that real-time human interaction.
So we also have a graph, a diagram which might make it easier to follow along with. But this is basically the assembly line architecture we're seeing from the LPU.
That's correct. So LPU on the right hand, on my left hand side, and on the right hand side, the GPU. You can see that in the GPU, the compute code is fetched from the DRAM, high bandwidth memory, HBM. It operates on it, puts the intermediate data back into the DRAM, and it has to do that thousands of times at a time. That's why you see that blinking. You can imagine, so this already looks as a hub and spoke design. You can see there's a switch in the center, and you have the 4 GPUs on the side. Now, interestingly, even within the GPUs, the various small cores that you see are also hub and spoke design. As opposed to that, on the LPU side, as you can see, we map the compute volume once, and after that, the computation, the tokens in the case of LLMs, are processed very much like an assembly line. And that is what makes it low latency, better throughput per dollar, and better throughput per watt, all at the same time. So it's an and, we don't do ors. Another way of looking at it is, this is, if you innovate on a given solution surface for the geeks, solution manifolds, you are doing trade-offs. But given the problem that we are solving is quite different than when the GPUs and the CPUs started, and we really have to emulate what human beings actually do with their eyes and ears. We have chosen a solution manifold that allows us to do ANDs, low latency and high throughput per dollar and high throughput per watt. Again, for the geeks, the other difference, the way of looking at it would be the GPUs scale in time. You get the compute code and the weights from the HBM and you loop over it thousands of times. So you scale in time. The larger the problem, the more you're going to get those partitions from the memory and do that. We scale in space. We map it once. We scale in space as a pipeline. And we just, after that, the compute just flows through.
So one of the key benefits, the unique selling points of Groq is this ultra low latency.
That's correct.
Everyone's going to get access to because of this LPU architecture. So I recently read an article about Groq mentioning that they don't want to just be a hardware company, and it came out with a Groq Cloud product, which lets people use the open source models that have been deployed on Groq. Could you speak a bit about this?
So as a new solution and architecture that we have enabled, you can imagine that in the infrastructure space where the spend is pretty large checks, and no one wants to make a large bet on something very new. So the one way of breaking into such a market is you enable end-to-end. So in that context, what we have done is think of it as 4 business units within Groq. One of them that takes things to the end customer, that's Groq Cloud. The other one to serve the compute system need of the government. We have a government business unit. Similarly for the enterprise, for the compute system. It's not a cloud. It's not API for the various public models. The third one, of course, is enabling the largest of largest hyperscalers. On the Groq Cloud front, at this point, we don't make our own models. We don't want to make our own models. We would rather avail of the ecosystem. And in the open ecosystem, the open source models that are available, we are hosting them today that can be accessed through the APIs as you would access OpenAI or Claude from Anthropic, and so on and so forth.
So as an engineer myself, I can see immense benefits of just using something that has incredible inference, especially for stuff that's wearable related. Because we're doing all these, we're building all these applications where you're giving it a lot of context, and then you have to wait for the whole output to finish. But I see a lot of value in, instead of me having to cache responses, I could potentially just run inference multiple times. And if it's 10 times cheaper than using Nvidia, I see a lot of value in this. Something very interesting you mentioned was that there's an energy benefit as well to using this. And I keep seeing these discussions now going around where people are discussing that energy is the new currency, because all compute is very expensive and you need energy to run it. Mm-hmm. How much better is the energy consumption on Groq's architecture?
Minimum 10x, and again, we don't put the final numbers because and we are rounding it off to 10x. Everyone likes 10x numbers. Minimum 10x, and as we announce things, you'll see where we go from there. And the reason for that is, so you can see that in the GPU architecture, you have to get the compute code from that external warehouse, the HBM. That takes a lot of energy. It turns out that the compute energy is few orders of magnitude lower than having to go back and forth through the HBM to get that data. And on the other hand, once we have mapped everything, a compute volume to our sequence of chips here, we do not get penalized for that energy at all. Assembly line allows you to use the hardware resources and the energy a lot more efficiently. There's a reason why most industrial production today is done with assembly lines. So you can expect actually better and better energy and cost structure.
So Nvidia had a pretty big announcement last month at GTC.
Right.
They announced the Blackwell platform.
Mm-hmm.
Is Groq concerned?
No. So the way, again, so around the time when Ford introduced the assembly line, actually, let's go to even a bit earlier than that, when the automotives were seen as a viable mode of transportation, the response from the buggy manufacturers were, okay, automotive guys, you have a 5 horsepower engine, we'll put 2 more horses. So horses as in horses. There were 2 horses plus 2 horses. So 4 horses, we are almost there, faster and bigger buggies. We'll catch up with you guys, but we know what happened with the automotives. The architectural space for the automotives allowed for better optimization, and it allowed for the automotives to go from 5 horsepower to 10 horsepower to 20, and then came the V8, but was 50 horsepower. So the announcement for Nvidia was bigger and better buggies. We are just getting started with the automotives. They didn't catch up even now. We don't think they will catch up. So the automotives outran the buggies. We all know the history. GPUs are good for certain kind of things. They were created for graphics. They're good for parallel load execution, where for training, for example, they work well. You don't want to use tools that were done for something else when you have a better architectural solution.
Do you think, so NVIDIA's secret sauce is CUDA, their kernel. Do you think that could also be something that's holding them back if they were to pivot to something like an LPU?
Actually, so CUDA is the reason why we think of NVIDIA as a hardware company. But the reason NVIDIA has the top dog space today is because of their software. AMD, that manufactures the other GPUs, and their hardware is at least as good as NVIDIA's, if not better. The reason AMD is not adopted well is because NVIDIA has had 15 years of creating the CUDA ecosystem. And for the GPU architectures, whether it's AMD, NVIDIA, or Intel also has GPUs. Unfortunately, to get good utilization from that hardware, from that architecture, you need to hand tweak the kernels. The compiler out of the box doesn't give you good hardware utilization. What that translates to is your cost structure is going to be more expensive, your power is going to be more, and to avoid that, you need actually hand-coded kernels. We have avoided that problem completely. We actually started from the compiler side. We didn't start from hardware up. We looked at the whole problem and then mathematically reduced it to the bare minimum that we needed to put in the hardware. Our hardware is, again, for the geeks, it is a one-dimensional bin array, and that translates to a problem of 1D packing, one-dimensional packing, as opposed to the GPUs, which is on the chip is a two-dimensional packing, and when you put the network together, it's a multi-dimensional bin packing. The 2D and multi-dimensional bin packing is a NP-complete problem. So the geeks here would recognize that that's a difficult problem to solve. 1D bin packing problem is not an NP-complete problem. So our compiler works straight off the box with high hardware utilization. We were able to bring up models that would take NVIDIA 6 months to 9 months to get good utilization in a matter of days. And that's another reason why the new architecture, we can actually ramp up and bring up workloads that other folks cannot, which AMD cannot today, even with their good hardware that they have.
So a lot of people that have actually heard about Groq here probably heard about it because everyone on Twitter was posting pictures of going to Groq chat and as soon as they finish typing something, pressing enter, as soon as they like finish typing, the text just starts generating. It's incredibly fast. Right now, I believe Groq Cloud only supports Gemma, Mistral, and Llama. When do you what new models are we going to see on Groq Cloud?
It's all the popular models. So it depends upon the ecosystem as to what the ecosystem votes as the popular ones. We can only do open source, and obviously some of the folks would like their proprietary models to be hosted, but if there's enough business, we'll entertain that.
That's interesting. What do you think? What is next for Groq? What should we all be looking forward to over the next year?
We don't give targets. What you can see, I'll reiterate, the automotives are only getting started. We are at 10 horsepower. I think the buggies are at 2 horsepower, maybe 3, 4. You can imagine what happens when the automotives put on the V4s and the V8s. This is not, what we have here is not just for machine learning. This is for high-performance compute. We believe this will change the computation for linear algebra acceleration in general for large compute significantly.
Awesome. Well, thank you so much for taking out the time to be here.
Thank you.
I hope you all learned something today. And awesome. Thank you.